So we've just seen then the result for the replacement for this sum that appears over and over again for us, right? For the case where we have a thick chunk, right, something where we're going to want to do a volume integral, that does come up, but more often we're actually dealing with a thin wire. So let's think a little bit about how we would re-represent this relationship in the case of a thin wire. So for a thin wire, we will have a situation that then looks something more like the following. So for a thin wire, I'm going to have, again, some direction to my wire. He's going to be fairly thin and narrow. He will definitely have some cross-sectional area A here that I'm representing. He's going to have, if I think about a little chunk of my wire, he will have some length, which I will call then delta L, like that. And in a thin wire, one of the nice little things is that the current density, you will notice, has only really one direction that it can flow in. It has to be along the wire. So there's my current density, J, flowing along my wire, like so. So now, because this wire is so thin, right, and by thin here, I have a very specific idea in mind. So let's be very careful when we specify that. By thin, we mean that the magnetic field is constant, or nearly constant, right, to a good approximation, over the cross-section, over the wire cross-section. So in essence, we can integrate across the entire wire cross-section. If that's the case, right, then I can make the following observation, that the current density times the volume of this particular chunk, right, will equal the current density J, the volume of my chunk of this little wire here that I'm considering now, little chunked up wire. The volume is just the area times the length, so that will be A times delta L. Now here's where something interesting happens, of course. Notice, the current density is current per unit area times area. That will give me the magnitude of current. So I will have I for the magnitude for JA, and then of course you multiply by delta L. So that's the magnitude of this vector. I still have to specify the direction, though, because it's a proper vector that I'm trying to describe. That's the magnitude. For the direction, I know that that's in the direction of the flow, right? That has to be in the direction of J, of the flow. But the flow, notice, because the wire is so narrow, we know has to be oriented along the wire. So the flow is actually just as the same thing as the direction along the wire, the direction of the flow, or which would equal the direction of the wire. So that gives us a nice little opportunity to define a new vector that will be very handy for us. I will call this I. And then this length along the wire, I of course can turn into a vector that gives me the direction of the current flow along the wire, like so. And I'll give it the magnitude delta L, but I will call it delta L vector to indicate that it's a vector along the length and has a length delta L. When I do that, then my formula simply becomes that this J delta VC equivalently can be represented as I times delta L vector, or, of course, if we take the limit in order to form an integral later on, this would be the same thing as I times dl. So that is yet another replacement where we can use in order to form integrals, but now in this case, this is the replacement we would make for a thin wire. So if in a thin wire situation, we have an expression where we have to do a sum over particles, right, that go like Qi times Vi. The result of that sum, again, can be replaced by an integral with I dl. So I'm going to put another box around that. Another handy result, but this is the case for wires, as we've been emphasizing. So in either case, then, we now are prepared to give a final form for the total magnetic force.